Okay, we'd like to really just review some basic properties of complex numbers, and we're going to be doing that over the next few videos. We had a definition going way back to your Algebra 2 class that if we had the square root of -1, we would call that I, the imaginary number I. Now if we were to square both sides, very quickly we could see I squared would equal -1. I could take I to the third, and that would just be I squared times I. I squared is -1. -1 times I, of course, is just -I. I to the fourth is simply I squared times I squared. That's -1 times -1. So that is simply a +1. From here, we're going to see that we are in a cycle. I to the fifth is really I to the fourth times I, but we just said that I to the fourth is 1, and 1 times I is I. So we're going to just repeat these values that we saw previously. We have a cycle of length 4. And what we can see are these values of I, -1, -I, and 1, continually repeating. And this is just going to repeat forever on as we were to increase higher powers of I. Like we saw I to the 6, I to the fourth is 1, 1 times I squared, I to the fourth times I squared, I'm so sorry. This would be 1 times -1. So you could see we're right back in this pattern. What you can see, though, is that when we've got this cycle with I to the first, we can think of this as a remainder of 1, a remainder of 2, a remainder of 3, and a remainder of 0 if we were to divide by 4. And for example, we could say find I to the 47th power. Well, we certainly don't have to work this all out the way that we had done previously. What we can do is say, well, let's see, 4 divides into 47. Well, this would go in 0 times, drop down a 7. And right here we'd say 11. So 11 times 4 would be 44. But as we continue this on, you can see just like we did in elementary school, this would be a remainder of 3. With a remainder of 3, of course, we'd have -I. So this would simplify very quickly to just -I. So that's valuable in case you ever needed to do some work with I to a power. But let's talk about a complex number. That was just an imaginary number. A complex number is going to be a real number plus an imaginary number. So we'll have a real component and an imaginary component. And A plus BI is the general term. B, of course, could be negative. We can add complex numbers. We could have, say, 5 plus 3i plus -2 plus 4i. And very quickly we could see that really we will add the real components. We'll add the imaginary components, and we'll be good to go. We can also subtract these numbers as well. And the wonderful thing is the behavior is going to be just like we'd see for like terms. Distributing that negative, we'd have 5 plus 3i. This would become a plus 2, and then a minus 4i. You could see this would be 7 minus I. What else could we do with complex numbers? Well, we could multiply. And we could take in the same problem 5 plus 3i times -2 plus 4i. And just foiling this out, 5 times -2 is -10. 5 times 4i is 20i. 3i times -2 is a -6i. 3i times 4i is 12i squared. This I squared, however, is one of the most commonly occurring values that you're going to see with complex numbers. I squared, we're always going to immediately turn into -1. Now, because this shows up so commonly, a lot of teachers will just say cross out the I squared and change the sign out in front. That is certainly viable. You can do that. -10 plus -12 is -22. 20i minus 6i, well, that would add up to 14i. So you can see that you can, in fact, multiply two complex numbers together. Sometimes you'll even see that when you multiply them together, you wind up with a real number. And if you were to say multiply 1 plus 2i times 1 minus 2i, very quickly kids might notice, hey, these are conjugates. What do conjugates multiply into? A minus b times a plus b. Well, hey, that's a squared minus b squared. This would be 1 squared minus 2i squared. Well, what is 2i squared? 4i squared. Like we were just saying a moment ago, you could cross out the I squared, change the sign, 1 plus 4. Hey, look at that. Two complex numbers actually are going to multiply out to just a real number. Now, division is also possible with complex numbers. Division, what you could see is if I gave you 3 plus I divided by, let's say that I gave you 1 minus 2i, just to give you something like that sort. When we're going to divide, the way you want to work this out, I is really a square root. It's the square root of -1. And if you go back to your algebra days, what you would see is if I gave you something like 1 plus radical 5 all over 2 minus root 3, if I gave you something like that, you'd multiply the top and the bottom of that fraction by the conjugate of the denominator. We're going to do that right here. Why do we multiply by the conjugate? Well, we just saw a moment ago that the conjugate is going to allow us to get a difference of squares. That is how we can multiply two complex numbers together and get a real number. The i's are going to drop out. Now up on top, we could say 3 times 1 is 3, 3 times 2i is 6i, I times 1 is just an I, and I times 2i, of course, is our 2i squared. Down below, 1 minus, well, here's our 4i squared. Hey, we just did that a moment ago, didn't we? Down below, we, of course, have a 5. Look, up on top, I squared is just going to make that 2 a negative. 3 plus -2 is 1. 6i plus 1i is 7i. A lot of times we'll just separate this into a real number and an imaginary number. That's really the convention. And that's where we're going. Okay, so from here we could talk about several other things. We could talk about the magnitude of a complex number. The magnitude is going to be the absolute value. Like, for example, if I gave you the absolute value of 3 plus 4i. Now, before, the absolute value that we were using just with real numbers, that was measuring the distance a number is from 0. The absolute value here is measuring a distance as well. And what I want to point out to you is that we have really a way of graphing a complex number. This is called an Argonne diagram. An Argonne diagram will have the real axis on the x-axis and the imaginary axis on the y. So when I was looking at 3 plus 4i, this can be thought of as a point, believe it or not. We can say, well, my goodness, this is our ordered pair, 3 plus 4i. 3 steps to the right, up 4. And if you remember your geometry, well, this distance right here is going to be 5. From the Pythagorean theorem, of course, you could call that a d if you'd like. D squared equals 3 squared plus 4 squared, and then take the square root of it. But my goodness, I hope we know the most famous Pythagorean triple of all, the 3, 4, 5. So magnitude is always going to refer to distance from 0. What else can we have? Well, we can have another way to represent a complex conjugate. If z is equal to a plus bi, in our contests, most of the time we'll have z bar being the complex conjugate of it. So that's just notation. So in the time that we have remaining, I'd like for us to do a quick problem. Let's say that we've got this for an example. Let's just say that if w is equal to 2 plus 8i, find the magnitude of w plus 2w conjugate. Well, how would we do that? Well, the conjugate, of course, is going to be 2 minus 8i. And 2 times that conjugate, well, that's going to be 4 minus 16i. So if I were to work this out, I'm going to have w is 2 plus 8i, but 2 times the conjugate is 4 minus 16i. Adding inside, these are really still thought of as grouping symbols or parentheses. We could very quickly come up with 6 and then minus 8i. Now, once again, we could graph this. We could say, well, my goodness, I'm going to go 6 steps in the real positive direction and then down 8 steps in the imaginary. And it would be a 4th quadrant kind of an angle. Once again, our distance could be found via the Pythagorean theorem. But again, if we're really on our toes, if we're remembering the Pythagorean triples, the 3, 4, 5, if I doubled that, we'd get 6, 8, 10. So this magnitude would actually just be 10. And magnitudes, of course, are always positive. They are measuring a distance. So even when you see negative values for your components, the end result is a positive. Well, maybe one other thing to at least introduce you to right here. Since we have the Argand diagram, something worth talking about is we do have another way to represent points. Look, we could have this point over here. Let's just say it's our, x plus yi. So we'd be going x units over to the right, y units up. Another way to represent a point is through polar form. In polar form, and this is something that's studied in Calculus BC, polar form is thinking of a point primarily as a radius and an angle. We've got this angle right here, and we've got r. So what we could do very quickly is notice the Pythagorean theorem definitely holds true. R squared is equal to x squared plus y squared. But from trigonometry, we could say the sine of this angle, sine of theta, is y over r. Or equivalently, that y is equal to r sine of theta. Also, very, very quickly, we could say that, well, my goodness, x is going to be related to the cosine. The cosine of theta is equal to x all over r. So x is equal to r cosine of theta. Well, let's go ahead and see if we could fit that in. If x is r cosine of theta, and if y is r sine of theta, and we can keep our imaginary component over here just for the moment, how about we factor out r, and then we will have what's known as cis notation. We'll put the I out in front. And this is the polar form of a complex number called cis notation. We're going to be able to use this idea a lot in the future. We'll be picking up again in video number 2.